AV man?
Yeah, I think you're on.
Oh, cool. Cool. Right. Welcome, everybody. Thank you so much for coming. It's good to see so many people here. We've got some great speakers lined up. I'm sure you've heard of them. It's really exciting stuff we're going to be talking about. So I'm not going to waste anybody's time anymore. I'd like to introduce Steve Dodson, CTO and founder of Prelert. So welcome, Steve.
Great. Hi, guys, and great to see so many people here, and thanks, Sainsbury's. It's a really great venue. So what I'm going to talk about today is anomaly detection using Elasticsearch, and I'm going to try and go into some technical detail about our experiences when trying to build out a product that can detect anomalies and look for behavior analytics and machine data. So just to start with, who are Prelert and who are we? We're an Elastic partner. We've recently released a product called Behavioral Analytics for the Elastic Stack, and that's an application built on the Kibana UI framework. I'm going to do a demo of that product at the end of this, so I need to make sure that I don't waste time. We've got customers, and our products are also OEMs by people like CA, Blue Coat, and others into their stacks to provide behavioral analytics and anomaly detection for those type of products. Now, some of the dev team are here from our London office, and they wrote this product. I'm here presenting, but sort of they're the real guys behind it. And I think if there's really technical questions, I'll defer some of those questions to those guys. So, in sort of summary, what I'm planning to talk about is, why is anomaly detection useful? Sort of why did I start Prelert, and what was the premise that I started it on? I'm then going to deep dive into some anomaly detection approaches. Now, if you're familiar with the space, you may recognize some of this, but I'm also going to go into some real sort of technical depth about what we do at Prelert and some of the approaches we use. And then, because obviously this is an Elastic meetup, I'm going to go through how this aligns with Elastic and how you can get it to analyze your data in Elastic and where the value is there with a demo. Okay, so overview of the problem. So when I started the company, I spent quite a lot of time in some places like this, one in London, one in Virginia. These are operation centers and typically have a load of screens and pretty dark and people sitting there. And what I learned, I'd previously worked on products in the network management and the storage space, and those products were struggling to come up with good alerting. They were struggling to come up with without false positives, without false negatives in terms of alerting. And really, the key questions that people are asking in these operation centers are, is my system okay? You've got so much data, you've got all this log data, it's very difficult to understand whether it's good or bad. So it's really, is my system normal or has something changed? And if it's changed, tell me why. So for instance, if the response times go up or the error rates go up and so on, something's changed and I need to know which part of the system I need to know which part of the system is causing this and then fix it as soon as I can. And to do this, you obviously need to collect and store machine data, and that's great. And Elasticsearch is a great tool for doing that in terms of consolidating your machine data and providing effectively a platform where you can search that data and get value out of that data. But really, sort of where we sit is we're not focused on collecting or storing data. We've deliberately just done the analytics part because originally sort of my background's in that type of space, and we've also got some really good developers and R&D guys in that space. And what I believe you need to solve these to answer these questions is an understanding of normal behavior. And once you understand normal behavior, you can see what's abnormal. And I'm going to go through examples of that and hopefully get you to understand what I'm trying to talk about here. Okay, so first example. So this is actually real customer data. So this is a big multinational retail customer, and they had a very simple use case to start off with, in that they get orders, they get a certain rate of orders per minute, and it's fairly consistent. And if they have an application error, that drops. And that costs them money. So literally, they're losing hundreds of thousands if it drops for 5 minutes. So they need to monitor this very closely, and they need to understand if this changes, and if this changes, what's going on the back end. So what we do is we model these type of signals, and I'm going to describe how we do that later in the talk. So we effectively model these type of signals, and these are the sort of baselines we can produce that actually model these type of systems. And the value to the customer ultimately is a set of warnings and a set of alerts when things change. So in this case, there was actually a precursor. There was an application error that was a precursor to a significant issue that sort of took them out for about 4 or 5 hours on one of their point of sale systems. So, I mean, that's the sort of use case we're talking about, where we're modeling these signals accurately, then providing them with high fidelity alerts based on changes in these signals. So that's sort of like use case number one. It's a single time series, univariate. But really, the sort of the holy grail, and this is sort of where we're trying to get to, and where we're getting to with Prelert, is that not only do you understand that the system has changed or a KPI has changed, but why it's changed. So you not only analyze the KPIs, but you analyze a lot more data, the back-end metrics, the logs and log metrics, and so on. And then if there's a KPI change, you can tell them, well, it's this and this. And we don't know the exact cause. We're not saying this is the root cause, but what we're saying is these things are potentially related, and these are probable causes, and you can then go and try and triage the problem as quickly as you can. Okay, so that's sort of an overview of a use case, and now what I'm going to go into some methods that you can use to do this, and critique some methods based on the evolution of the products we've had over the last few years. Okay, so if we just think about that first time series, really, just starting at a really basic level, what you see in a lot of operation centers is eyeballing is one of the primary ways of analyzing this data. So, one of the banks that I was actually in an underground data center doing this with, they actually ran out of screens to put stuff on. And their solution was to put more screens on and actually extend into the ceiling to put more screens on so they could eyeball more charts. Now, I mean, that's one way of doing it, but I'm going to go into this. Maybe there's a better way of doing it that will allow you to actually understand more data and analyze more data. Also, there's things like static thresholds. These have been around for ages. I worked on the IBM Tivoli products, and they've been around for ages. But really, what I'm going to go into more detail are things like behavioral analytics, where we can actually learn the behavior of the data from the data. And this is where you can do more dynamic thresholds and actually understand what's normal in the data and what's abnormal. Okay, so first thing about eyeballing. Right, so where's the anomaly in this? This is real data. There's an anomaly in this that was actually an issue with a storage device. And this is often sort of what you're up against on some of the data, in that I can only, for a start, if I look at charts, I can only see a certain amount of the data. I can't see all the data that I'm collecting in Elasticsearch. Also, depending on your aggregation strategy, depending on the granularity of your charting, things can look different. And also, it's expensive to have people looking at charts 24/7. Yeah, if you can alert them, if you can page people, then it's going to be a lot more effective than eyeballing everything. So this is the anomaly. And the reason this is an anomaly is that it's the only one sort of during working hours. The rest all the other spikes are actually at a fairly consistent time, and that was actually a batch job that was running overnight, but that was during operational hours, and that caused actually some interrupts in the system. And if I overlay some baselines on top of this, and these are baselines that we automatically create, you can a lot more clearly see that doesn't conform to the standard baselines of the product. Okay, so another chart. So you have to aggregate data. This is there's a lot of stuff here, and if I draw it as dots, where's the anomaly? Where's the anomaly in this? And this was an interesting example because if you aggregate this data into 5-minute buckets and display it, you get this. Yeah, and so the customer said, oh, well, you missed this anomaly. You missed this anomaly here. And the reason there's a spike there is actually because of your aggregation strategy, of how you've bucketed the data. Because if I drill into that spike, and hopefully this isn't too confusing, there's actually not that many points in a bucket, but there's sort of a consistent consistent sort of 4 or 5 or points in the bucket, but in this bucket there's only 1 point. So the point itself isn't anomalous, but there's not that many points in the bucket, so the average looks a lot higher. Okay, so when you're looking at charts, you need to be, just be careful how you aggregate them and be careful what you're seeing, because you potentially see things which miss anomalies, which I'm going to show you later as well, or which show anomalies which potentially you're not interested in. Because this is an anomaly, because it's the only space where you've got a low count, but it's not an anomaly in the actual value in response time. Okay, so I just want to get through the first simple methods, and one thing that's really really is actually still very useful is if you know a limit, you can put a static threshold in there. If I know that my response time should never be above 50 milliseconds, and I want to be alerted when that happens, you can do that, and that's great. But often the systems we're dealing with millions of metrics, and those metrics are behaving differently. And to actually manually set static thresholds for that is just impractical. Yeah, so what we're really driving towards is some way of modeling the data to create these type of dynamic thresholds or behavioral analytics to understand the data. And it's this sort of thing that I'm going to describe about how do you do this and the approaches you've got to creating these dynamic thresholds as the data is being streamed in. Okay, so general approach for doing this, and this is sort of some of the text we use is, what we call the approach we use anyway is unsupervised machine learning. Up front, we're not creating a supervised model. We're trying to create the model as the data is being streamed through us. And really, the goal of all of this is really to create this predictive model based on what we've seen so far. So we've seen a certain amount of history so far. Now that will give us a model which will allow us to calculate the probability of the next point. And really that's what we're trying to do, and that's sort of the goal behind what we're doing. So, a way of doing this, and the simple mathematical way of doing this, is to fit a normal distribution. So I can fit, value, plus or minus 2.5 standard deviations. So on this data, these are the sort of baselines you get, and these haven't been created as the data's been streamed. These have been created as the data's a batch, which is another problem. But if I stream the data, I can create the means and the standard deviations as it goes across, but you still get quite a lot of anomalies in this system, which are false positives. And so why is this? Why are our Gaussians not particularly effective at modeling this data? So if I plot this data as a histogram, then really sort of a naive statistical way of thinking about this is I want to try and find a distribution that models that histogram reasonably. So if I have a normal distribution there, it looks okay, it doesn't look too bad, but the type of distributions that we automatically fit to these types of data are slightly different. And the key point is that anomalies are in this part of the distributions. It doesn't matter so much about the bit up here, but these are the bits you need to model accurately, because these are the anomalies. This is the bit that you need to model correctly. And so if I actually look at sort of the errors and the probabilities that you get from a normal distribution and from a more sort of correct fat-tail distribution against a reference probability here, you can see that the error in terms of how you calculate the probability increases significantly in these tails. And what this means is you get false positives and false negatives by using this approach. And if you're talking about millions of metrics, these just scale up. If you're trying to find out, is a million metrics anomalous at one point, if you've got these errors in your probabilities, it's just going to escalate and escalate until you get something which isn't particularly usable. Okay, so how do we do it? How do we solve this problem if we're not using these methods? And this is sort of like when we first started the company, first started the product. We were looking at, well, there's lots of different ways of doing this. I mean, there's lots of different techniques being used for anomaly detection and time series analysis. I mean, you could send charts to Mechanical Turk. It's probably not a great way of doing it, but and there's obviously a lot of interest in deep learning and so on at the moment. So how do you choose an appropriate method? And really, what we went through are sort of what are the requirements for the approach you choose. And this is sort of one of the key things I want to try and get across. and it's just words on a slide, but I want to try and get across that, this is, in our view anyway, this is the sort of things that you need to satisfy to have an effective method. So the first thing is, you want the system to operate in real time. Now, you're getting this fire hose of machine data, whether it be from Elasticsearch or another product, and you want to understand and alert when something changes. You want to do that in as timely a fashion as possible, because that can cost the user money. You don't want to have to go and offline batch analyze stuff and come back later with a result. Accuracy is obviously key. So false positives and false negatives are things you want to try and minimize. Now the next point, robustness, is sort of the one that I think is actually quite hard, because if you're dealing with a lot of different time series, a lot of different metrics of machine data, then they behave differently. You have things which are really spiky, you have things which are smooth, you have things over different values, you have things which are counts compared to metrics and so on. And what you want ideally is a system that is robust to that different types of data and can create effective models regardless of the data sets being shoved in. Then, ideally it's got to be easy to use. You don't want it to be really, really difficult for people to configure this and use this, or then have to set a load of parameters to try and use this. And then finally, scalability is key. If you choose certain approaches and such as, say, HTM type approaches, then you'll really struggle with the amount of memory usage it will take you to model particular series. And as I said, really the goal here is to model millions of concurrent series on reasonable hardware. Okay, so how do we go about it? And I'm going to get into a bit of the maths behind what we're doing here, and we've got papers on this. Is if we take the data, effectively, what you're doing as a product is you're taking the data as it's being streamed through it. So you start over here, and you haven't seen a lot of data. So what can you infer? What model can you create? And as you see more and more data, hopefully you can make more accurate inferences about what the data is and how to model it. So these are actual descriptions of models that we create, first sort of initially, and then sort of later on in this data. And you can see that they're not just simple Gaussians. They're actually mixture distributions. This is actually a multimodal distribution, and they're more complex distributions that we create. And the other thing is that we use Bayesian model selection to actually determine which models to use, which allows us to understand the uncertainty in the data and how much data we've seen. So based on that, if we've only seen a bit of data, we'll have a wide variance in our distributions that will narrow over time as we become more and more certain about the data we've seen. So plotting that another way is, this is the sort of evolutions of our models on this data. And you'll see that, at this point here, we've got to the point where, yeah, that's great. We've actually seen enough data to actually make a decision to say a multimodal distribution will fit this better. And this is sort of just one of the things that we found to actually represent this data as a model that we need to do to reduce false positives and false negatives. Okay, so that's one of the most technical bits. So I'll get on to now really what are probably more real data. Now, I showed something non-periodic there, and this is how most data is, unfortunately. Yeah, so most data has this sort of seasonal pattern. It may, it's got daily patterns, it's got weekly patterns, and so on. And this adds further complexity in terms of modeling this. Now, this is actual real data from one of our customers, and they marked up this data as having these anomalies. So there's a slightly high peak, but it's this step change and this drop here and this unusual day here are some of the key things that they viewed as the key things for them operationally in this data. Now, I talked a lot about fitting these complex distributions, but the problem is when you fit just a complex distribution across this data, this is the sort of thing you get. Now, okay, in this case, I've fitted a reasonably simple distribution, but you can see that it doesn't account for the time variance of the data. It's not accounting for the weekly and daily behaviors of this data. So how do you do that? So here's a load of false positives, false negatives, and so on that you get just using a single distribution or a mixture of distributions on that data. So, really what we try and do is say that this type of data is not just made up of some type of distribution modeling the residual, but there's a trend in it. And what we want to do is try and construct these models as the data is being streamed through us, construct a model of the trend, and construct the distributions as well. Now, this is sort of a visual representation of us actually doing this on this data set. And just to explain this, the black line is the raw data, and the blue and red lines are effectively sort of some bounds of Prelert's probability distributions as the data is being streamed in. And as you see that when we first see data, we don't assume that it's weekly or we don't assume that it's daily. Now, this whole robustness to arbitrary data means that we can't upfront just say it's going to be like this. So we want to try and learn the behavior of the data from the data as it's being streamed through. So initially, we don't detect any periodicity. But after about 2 days, we can make an inference that this could be daily. So we start fitting a daily trend to the data plus our residuals. And as always, as often happens in this sort of set of data, as we see more data, our models become more accurate. Okay, so daily periodicity is okay, but a lot of stuff's weekly as well. So we do a similar thing with weekly periodicity, where as we see more data, as we see around sort of after sort of two and a bit weeks data, we can make an inference that this could be weekly data, and start modelling it even tighter. And you can see the green arrow here is actually the variance in the data that becomes a lot tighter as we see more data. And really, this is sort of the state we want to get to. If we want to detect those anomalies that I showed before on the previous slide, that's sort of where you need to get to actually detect those and understand those. Okay, so there's lots of ways of doing these sort of trends, and Holt-Winters is a relatively simple way of doing extrapolation, sort of exponential filtering on the data. But if you're using the predictions from Holt-Winters, then unfortunately, if you're using it to extrapolate, it can be very useful, and it always looks as if it fits the data very well. But in our experience on certain types of data like this, you end up with quite a lot of false positives because it's overfitting the samples. Okay, so here's the data, and here's Prelert results on it, but that's sort of to be expected because we're presenting this, and I just went through that example. Okay, so I've sort of rushed through that, and really what I wanted to get onto, because it's an Elastic user group, is a demo of the product and how it fits in with the Elastic stack and how it fits in with machine data. So to do this demo, I'm going to take a very similar example to the one I described before, where I've got key performance indicators, and I've got back-end metrics as well. And I'm going to set up live a system to analyze some key performance indicators, and then show you how we can correlate that to some back-end metrics to get to sort of root cause of a particular issue. The system I'm dealing with is actually based on a real customer system, but we've anonymized the data. And in this system, they've got a couple of servers, some VMs, and they're running different services. There's a couple of applications running. You've got a network switch and so on. You've got a back-end database, and one of the key performance indicators here is transactions per minute. Okay, and in this example, there was a drop in transactions per minute, which is one of the key things this customer was interested in. And their question was, why? Out of all this sort of infrastructure and applications on the back end, why was that happening, and how do I triage that? How do I get to the root cause of that as quickly as I can? Okay, so I'm going to attempt to run this through the demo. Now we've built our app on the Kibana UI. So this is Kibana, and this is just the data in Kibana. But we've also got this Prelert app in here. So if I go to the Prelert app, what we basically, in terms of terminology, what we do is we create an analysis job. So we've effectively create a configuration which allows us to stream, which allows us to take data from Elasticsearch or another source, stream it through our analytics engine, and then present the results. And we can do that in real time. We can do that on historical data as well. So to create a job, I can specify an Elasticsearch server. I've got this running locally. In terms of index, it's an index called ITOps, and I'm going to do this for the KPI type. And we've sort of automatically try and guess what the timestamp is in the data. So I've selected where the data's coming from. I'm just going to fill in some details. This is a job I'm going to create. I'm then going to configure some analysis. So this data is counts, and the counts are events per minute. So I put in that this is sort of a summarized value. So because if we know that the data has already been aggregated, we can actually model it more accurately. Because rather than modeling as a metric, we can actually model it as a count. So I'm now going to add a detector. I'm going to call it KPI counts. And then what I'm interested in is low counts. And there could be multiple KPIs. So I'm going to put a by field as KPI indicator. So if there's multiple KPIs, if there's 10 KPIs, we can model them together. We can model them in a multivariate sense as well, and we can come up with anomalies on that data in that set. Okay, so I'm bound to have made a mistake here somewhere, but if I click on save, that's a job I've created, and now I'm going to send the data through it. So operationally, if you've got data in Elasticsearch already, that's great, because what we want to do is provide you with real-time alerts through Watcher. And what we can do is, but if you've got data in there already, we can sort of bootstrap the process by going back in time, analysing the historical time, so we've actually up to speed and our models are as good as they can before we hit real time. So in this case, this data is not being streamed in real time, but I'm just going to start at the beginning of it anyway. I'm just going to say it goes up to whenever. Okay. So some nervous developers now. And so it's running, the data's going through, and that's it. So I've sent through, I think it's about a month's worth of data, and it's done, it's analysed. So what do the results look like? So this is sort of a presentation of our results, where we have the event rates we've seen, then we have these swim lanes that represent anomalies in the data. Yeah. Better? Okay. Okay, so what this is saying is that there's a critical anomaly in the data here. And this, again, represents one of the issues with eyeballing data, because